Hello everyone, welcome to the course Design and Analysis of Algorithms. Today's topic is recurrences. What is a recurrence? A recurrence is an equation that is used to represent the runtime of a recursive algorithm. So recurrences themselves are recursive. As we can see the recurrence equation given where t of n is the time required to solve the problem of size n. So on the right hand side there is a recursive call on the problem of size n by 2. So to solve for t of n, we first need to find the value of t of n by 2. And then to solve the value of t of n by 2, we first need to find the value of t of n by 4. And so on. So what is the actual runtime of an algorithm? To find the actual runtime of a recursive problem, we first need to solve the recurrence. We first need to find the recurrence relation, and then we need to solve it uh, to find an explicit formula that involves the value of n. So we need to remove the t part on the right hand side and we just need the n part on the right hand side. So we need a solution that just contains the n term on the right hand side without the t part. So a recursive method that calls itself recursively has two parts, the recursive case and the base case. The base case is very important as it tells us where to stop the actual recurrence call and solve the simplified version of the problem. So here is a generic form of recurrence relation where we have the base case which tells us where to stop the recursion, and then the recursive case which has two parts. One is the recursive part which tells us about the recurrence calls, and one is the non-recursive part. So A here tells us the number of times the function calls itself. So as we can see from the binary search equation, A will be 1. So in binary search, what is happening is that we have a sorted array and we split that into half. If we want to find a number, we either check if the value is greater than or less than. So either we will go to the right side or the left side. So in that case, the A will be 1. But in case of merge sort, when we are splitting the array into two halves, we are solving for both sides. So we are calling merge sort on the left and we are calling merge sort on the right. So in that case, the A will be 2. So B is the factor by which the input size is reduced. So as in case of binary search and merge sort, the problem is divided into two because we are splitting the array into half. So in that case, the value of B will be 2. So f of n is the runtime of each function, usually expressed in terms of big theta. So what is f of n is the non-recursive part of the recurrence equation. So this is what the actual cost is happening at each step or each recurrence step. So generally the recursive part is just the function calls, and once the function calls have been made recursively, so whatever is actually happening after those recurrence calls is denoted by f of n. So the base case is usually dropped as it is trivial from the definition, and we will write for this generic equation, we will write the recurrence relation as t of n is equal to a t of n by b plus f of n. So let's have a look at the factorial function. And factorial is the product of all integers between 1 and n inclusive. Given is a recursive function of factorial. As we can see, we have two cases, the base case and the recursive case. So the base case is trivial. It is either it has either a time complexity of 1 or it is happening in constant time. So whatever is happening here, interesting thing happening is in this line. So how do we find the time complexity and the recurrence equation to this problem? So as we can see that to find factorial of n, we need t of n time. So similarly, we can derive the time taken for finding factorial n minus 1. So if for n numbers time taken is t of n, then to find the factorial of n minus 1 numbers, the time taken will be t of n minus 1. So that will be the recurrence part, plus what is actually happening in each recurrence call is the computation multiply n with whatever we get in the as a result of this factorial call. So there is only one operation happening here. So the non-recursive part will be 1. So our recurrence equation will be as follows. The base case will be one operation, or you can write C here, which is constant time. And then to make the call of this factorial, we will have t of n minus 1 as it is happening on n minus 1 input size plus 1 because we are multiplying with n in each iteration. So this will be the final recurrence equation for the factorial problem. So in a generic case, if we want to write it, we can ignore the trivial base case. So our recurrence equation will be t of n is equal to t of n minus 1 plus 1. So let's have a look at another similar example of exponentiation. So in exponentiation, we have two numbers. One is the base and the other one is the exponent. So we have to find the base power of exponent, which means in this case x to the power of n. So we are given a recursive function of exponentiation. So it is very similar to the previous example that we did in the last slide. So this line here is of our interest in this case. So exponentiation is called on n minus 1, and then in the next iteration it's called on n minus 2 and so on. So we will have a same recurrence equation for exponentiation as we had for the factorial example, or simply we will have t of n is equal to t of n minus 1 plus 1. Let's have a look at a recursive algorithm to find the minimum numbers in the array. We are given an array of size n starting from 0 to n minus 1. In the base case, when n is equal to 1, that is the only value we have, so we will return that value. Otherwise, we will pick the last value of the array and recursively compare it with all the other values in the array. How do we actually derive the recurrence relation for a given algorithm? So now let's count the number of comparisons. So step 1, step 2 will run in constant time. Line 3 will not be considered because if the if condition has been performed and it's false, automatically the program counter will return here. So we will not count the else part. So in step 4, the recursive call will run on an input of size n minus 1 with the runtime of t of n minus 1. So the minimum operation will run in constant time. So this min function here is just comparing one number with the other number, that is the result from the find min recursive. So the recurrence for this problem will also be t of n is equal to t of n minus 1 plus some constant size, or we can just write plus 1. And the base case will be t of 1 is equal to 1. In the last 3 slides, we have seen the examples where the input size was decreasing by 1 in each iteration, and there was only one operation that was running in the non-recursive part. Hence, they all had a same recursive equation. Similarly, for linear search, we will have the same recurrence equation. So now let's look at the example of binary search for which the pseudocode is given below. For the binary search to work, the array should be sorted. So if we want to search for the value of x, so what will happen here is that we will have the lowest value and the highest value, which is the starting and ending index of the array. So that will be divided into 2 to find the mid part. So the array will be divided into 2. Now, after getting the mid value, so we will see what actual value is in the middle index of the array. And if that is the same as x, then we will return the mid value as we have found the value. Otherwise, if the value x is less than the middle value, we will call binary search to the left, and if the value of x is greater than the middle value, we will call the binary search on the right. So if we do the line by line analysis, we will see that all of these lines here are performing in constant time. So we have two recursive calls. One is on the left subarray and one is on the right subarray, which are both solving problem of size n by 2. But we have to note here that we have if conditions here. So either this condition will be true or this condition will be true. So one of the two will run. So what the recurrence equation will be is that A will be 1 because binary search is only called once recursively. So B will be n by 2 because the problem is of size n by 2 plus the constant operations that we are performing here. So that is the recurrence equation of binary search. Now let's have a look at merge sort, in which the array is divided into two parts, and merge sort is recursively called on the left subarray and the right subarray until the base case is reached, and then after finishing each recursive call on the way back, merge operation is called, which is doing the actual sorting. Now each merge operation is solving a problem of size n by 2, and as we studied in merge sort, the merge operation complexity is n. So there are n operations per iteration to perform the merge operation. So if we want to drive a recursive equation for that, in this case the A will be 2 because the merge sort is being called 2 times, and it should be T of n by 2. B should be n by 2 because it is solving for a problem of size n by 2, and the non-recursive part will be n operations. So the final recursive equation for merge sort will be T of n is equal to 2 T of n by 2 plus n. Similarly, for the best and average case of quicksort, the recurrence equation will be same. But for the worst case of quicksort, the recurrence equation will be different. In that case, the recurrence equation will be T of n is equal to T of n minus 1 plus n. That is left as an exercise for you to solve at home. Now let's have a look at a different problem, which is a Fibonacci sequence. In a Fibonacci sequence, each number is equal to the sum of the two numbers before it, starting from 0 and 1, which are the base cases. The pseudocode for Fibonacci sequence is given, where the base case will be just 1 or constant operations, and to find the Fibonacci of n requires T of n time complexity. Then for Fibonacci of n minus 1 will be T of n minus 1, and Fibonacci for n minus 2 will be t of n minus 2. And then the non-recursive part, there is just one operation which is addition of the two numbers that were returned from these recursive calls. So if you look at the recurrence equation, it will be 1 for the base case where n is less than or equal to 1, and then for n greater than 1 it's going to be t of n minus 1 plus t of n minus 2 plus 1, which is one operation, which is the addition operation here. To help you understand how to develop a recursive algorithm and derive a recurrence equation for a particular problem, let's look at this very interesting problem, which is the Tower of Hanoi puzzle. In this puzzle, we are given three posts which are labeled left, middle and right, and they are n disks placed in order on the left post. So the goal is to move all the disks on the left post to the right post while preserving the original ordering. So what are the rules of the game? Only one disk can be moved at a time. A move is taking one disk from post and putting it on another post on top of any other disk. So we cannot put a disk on the side. We have to put it in one of the posts. And we cannot put a larger disk on a top of a smaller disk. So these are the three rules which we need to follow to move n number of disks from the left post to the right post. So let's start off with one disk. If we have one disk, we can just place it from the left post to the right post and we are done. So one disk requires one move to move the disk from left post to the right post. For two disks, how many operations are required? So we start off with picking the smallest disk and placing it in the middle post. Then picking the largest disk from the left post and placing it on the right post. Then we pick the smallest post which was in the smallest disk which was in the middle post and put it on the right post, and in three operations we have moved the two disks from the left post to the right post. Now let's look at the solution for when the disk is 3, which is n is equal to 3. So we start off and move from left post to the right post. So that smallest disk goes to the right post. Then we move the disk from the left post to the middle post. And then we pick up the smallest disk from the right post and place it in the middle post. So at this stage, the first top two disks are in the middle post in order. So we can pick up the largest disk from the left post and place it on the right post. Then we pick up the smallest disk from the middle post and place it on the left post. Then we pick up the second smallest disk and from the middle post and place it to the right post. And then finally we move the smallest disk from the left post to the right post. So it took us a minimum of 7 operations to move 3 disks from left post to the right post. So now, how many operations would be required to move 4 disks from left post to the right post? We see here that as the number of disks are increasing, so is the complexity of the problem. So we will need to develop an algorithm that can solve this problem. Let's try to develop an idea for a recursive algorithm for this problem. In the final step, we want to move the largest disk from the left post to the right post. For that to happen, we need the n-1 top disks in the middle post. So we need a way to move n-1 top disks from left post to the middle post. So the base case is moving the smallest disk, which is easy. You can always move it to any post in one step. So the step number 1 should be to move top n-1 disks to post 2. And then in step 2, we move the largest disk to post 3 from post 1. And then move n- disks from post 2 to post 3. If you note, the step 1 is really the same problem, but with a fewer disk and a different target post. That is moving n-1 disks from post 1 to post 2. And step 3 is also the same problem with fewer disks and different starting and target posts. That is moving n-1 disk from post 2 to post 3. So this is a recursive algorithm. The terminal case is moving the smallest disk. We can move that directly without using the third post. And we can label the disks from 1, which is the smallest, to n, which is the largest. Interesting thing to note is that in the case when we want to move these 3 disks to this post, we can use the 3 post. That is because this disk, being the largest, does not violate any conditions or constraint of this problem, as we can place any of the 3 disks on top of this disk because this disk is the largest. Here is the pseudocode for Tower of Hanoi Puzzle. Input to this algorithm is count, which is the number of disks, and the 3 posts. So the second parameter is the start post, third parameter is the end post, and the last parameter is the mid post. So if the count is 1, that is if we have one disk, we can just move it directly. Otherwise, we will move the top end disk to the middle post. So the goal here is to move all these n- disks from the start point to the midpoint. So hence the end point or end post for this step will be the middle post because that is the target where we want to move all the disks. Then we move the largest disk to the end post. In this case, start post and end post will be the same and middle post will be the middle post. And then we move the n- disks from the middle post to the end post. In this case, the middle post will be the starting point, end post will be the end point, and start post will be the middle point. So what will be the recurrence equation for this problem? As you can see, for n disks, the time required is t of n. Then for n-1 disks, we want the time to be t of n-1. Since this n-1 disk moves are done recursively twice, hence our a for the recurrence equation will be 2. B will be n-1 because we are decreasing the input size by 1. And then the non-recursive part, we are doing just one operation, which is moving the largest disk. Hence, the final recurrence equation for this problem will be T of n is equal to 2t n-1 plus 1. So now let us perform the complexity analysis of this problem. As we have seen already in the previous slides, that to move one disk, one move is required. To move two disks, three moves are required. and to move 3 disks, 7 moves are required. From the developed algorithm, we can derive the number of moves required for different number of disks. So now let's see how many moves will be required to move 4 disks from left post to the right post. To move 4 disks from the left post to the right post, we will need to move 3 disks to the middle post, move the largest disk to the last post, and then move the 3 disks again from the middle post to the last post. So this requires 7 plus 7 plus 1, total of 15 moves. Similarly, for 5 disks, we need to move 4 disks to middle post, that requires 15 operation. Then we need to move the largest disk from left post to the right post, that requires 1 move. And then again we need to move those 4 disks in the middle post to the final post, requiring another 15 moves. So that is a total of 15 plus 15 plus 1 equal to 31 moves. From the pattern that is emerging from the required number of moves from different number of disks, we can derive the number of moves required for n disk. In this case, it will be 2 to the power of n minus 1. Hence, the complexity or time complexity for this problem will be 2 to the power of n. So through this problem, we learned how to develop a recursive algorithm, how to derive a recurrence equation, and how to get the time complexity. But in this case, we are just looking at the pattern and coming up with the time complexity. In the future lectures, we will see how can we solve these recurrence equations to get the time complexity. So some problems are computationally too difficult to solve in reasonable amount of time. So while an effective algorithm exists, we still don't have the time to wait for its completion, as we can see in this case. There are 3 methods for solving recurrences or recurrence equations. The first one is the substitution method, then the recursion tree method, and then the master method. So in the next few lectures, we will see how these methods work. That's it for today. Thank you.